rather than focusing on the derivation of the equations. So I've kept the equations on the board because we'll see them again and again, but from now on we're going to focus on the Navier-Stokes equations in the limit where you are looking at incompressible fluids. So the incompressibility constraint says that the divergence of the velocity is equal to 0, or equivalent the density is a constant. Conservation of linear momentum is that equation in the presence or absence of body forces. I'm not going to worry about heat anymore. If I'm the implicit limit, and we come back to a different setting, and the viscosity is equal to 0, and the equation simplifies some more, I said I will say something about vorticity, but in fact I decided I'm not going to, because there are other things that I'd like to essentially tell you about. So you can talk to me over lunch or in the evening when we go for our hike, and I'll be happy to tell you about that. Too small?
For sitting on top, it's too small.
It will encourage people to move
Just
down.
me, I have bad eyes.
Okay, because I heard thumbs up from there. Oh, I see thumbs up. All right,
Okay, fine.
sorry. Okay, so the implicit limit, as I said, corresponds to the viscosity going to 0. I won't really tell you much more about this than to say that there is a limit. You can actually analyze things of interest. But what I didn't tell you yesterday, because I ran too quickly and ran out of time, is the incompressible inertia-less limit. So if I have no inertia, that means the effect of density, inertia, mass is essentially irrelevant. So the left-hand side is systematically, I can drop. I will tell you about how you take that limit in a minute. But if I drop that out, and if I have body forces, then I have a balance between the gradients in pressure, which drive the flow, and the dissipation associated with motion of individual fluid elements relative to each other, and perhaps driven by some body force, and of course I have incompressibility. And the most important thing to point out about this limit is that unlike in all the other limits, where I have a u times gradient of u here in the implicit or in the Navier-Stokes, here I only have a term which is proportional to u. So therefore all velocities appear only linearly, and therefore in the constraint and in the equation of conservation of momentum, force balance. So these equations are linear. Okay? So Stokes flow, that limit corresponding to when inertia is not important, is linear, and so a lot of work can be done because you have lots of traditional methods associated with solving linear partial differential equations. And I'll show you some in the context of free surfaces, where even though the equations are non-linear, the PDE becomes non-linear, and that's because the free surface is allowed to essentially change. An important analogy which is worth pointing out, and that's also very nice because then you can solve two problems if you know to do the mathematics for one. And that is that if I replace the velocity by displacement, still a function of space and potentially time, but actually for now, if I'm thinking about only in linear elasticity, there's no inertia at all, so time is essentially not going to come in. If I replace the velocity by the displacement and I replace the viscosity by shear modulus, these equations mathematically are identical to the equations for an incompressible, linearly elastic solid. So you say if it's incompressible, how can you deform a solid? And again, I deform it exactly the same way that you essentially deform a liquid, which is incompressible, which is that I can change shape, but I can't change size. Okay? So mathematically, these equations, and in the lecture in the afternoon, I'll show you what happens when I put these two together. So this is the equation for the equilibrium, actually the dynamics of liquid when inertia is not important at all, Stokes flow, and if I replace the velocity by displacement, it becomes identical to the equation for linear elasticity. A sponge, which I'll tell you about in the afternoon, is a situation where I have liquid which is interpenetrating the solid, and so this is an interesting combination where I have the same u, but instead I better not, in order to make sure that nobody gets confused, I'm going to call u the velocity, sorry, u the displacement and v the velocity later on in the afternoon. What is the effective description now of a composite, which consists of a fluid plus a solid, which is what you and I are for the most part, mostly fluid. Okay, so this is where we stop, or almost where we stop, because then I said, in fact, instead of deriving the equation based on the balance of mass and the balance of momentum, and then using a relationship which tells us how to relate the stresses to the strains and the strain rates, you could have written down ab initio an equation which tells you how the velocity evolves and how the density changes. So, and I again don't want to belabor the point except to point out that this second equation, the first equation is the same as we wrote down yesterday, it's based on mass conservation. The second equation is essentially just the simplest thing that I can do when I write down an evolution equation for the velocity, and I keep all terms up to second order in space and up to cubic terms in the velocity, where all these coefficients, lambda 1, lambda 2, lambda 3, alpha, beta, d1, d2, and d3 are something that you have to determine either using an experiment or using some microscopic picture. This is not Galilean invariant. You can clearly see that, for example, because I have a bare velocity showing up. So if I change the velocity of my reference, then the equations will look different. But that makes sense if I'm thinking about self-propelled objects, because I'm essentially moving with respect to the environment. If I have bacteria moving with respect to the wall, if I have pedestrians moving with respect to the ground, and so on and so forth, it makes sense not to have Galilean invariance. And of course, associated with the breaking of these invariances, then I will have new pieces of physics. And I'm going to just leave it at that, because I hope that you will see this in some of the other lectures later on as you move more towards biological situations. Okay, so we've got the equations either using symmetry directly, symmetry and invariance directly, or symmetry and invariance based on the constitutive equation, which I've written down over there. What do we do now? Because these equations are nasty. So you have nonlinearities here, even if you don't have the other nonlinearities there. That's all the other terms are linear. What do? Well, we have to approximate it. You could do computation. A lot of people over here, I heard yesterday, are experts in computation. You could do some analysis, which is fairly limited, because you can essentially do this only in cases where you have exact solutions, and there are very few situations. Or you could do perturbation theory. Again, that's weak. Deviation from analytic solutions. Or you could use scaling ideas, the kinds of things that we saw already in the first lecture yesterday a little bit. And I want to focus on the third, because that's the only way I'll essentially be able to do something with you in the next hour and a half or so. Now, before I do that, I want to introduce perhaps one of the most powerful ideas in all of physics, and certainly in soft matter, which is the idea that every equation that you write down must have all terms which essentially have the same dimensions. A very simple idea, but a very powerful idea. Right? So in words, all terms, in any equation we write down must have the same dimensions. For example, in this equation over here, every term essentially corresponds to a force per unit volume. Okay? What can we do with that? Well, the first thing that you can do is you can reduce the number of actual parameters there are in the problem. And this has been in the physics lore ever since Galileo, formalized essentially by Fourier when he started thinking about heat conduction in solids, but really formalized even more broadly by Rayleigh and then by this person, Buckingham, who was, I think, an employee at NIST, or the precursor of NIST, 100 years ago. And he said something very profound, but also very simple. He said that suppose I have an equation. I don't care what form the equation is. It's algebraic, differential, integral, it doesn't really matter. And there are a certain number of variables. Okay? And these variables, each of them have certain dimensions. So for example, in the Navier-Stokes equations, I have the velocity, I have the pressure, I have the density, I have the viscosity, and that's it. In other systems, I have other things. So if I have a certain number of variables, n such physical variables, and each one of these variables depends on a certain number of independent physical units. For example, if I'm thinking about Newtonian mechanics, mass, length, and time suffice. If I'm thinking about electromagnetism, I might have to think about voltage and charge and so on and so forth, capacitance. But of course, there are mechanical analogs, and so I have to convert and I have to ask which independent units do I use. But nevertheless, suppose I have a number of independent physical units, which is k, I have a number of physical variables, which is n, then you can reduce this equation, not in terms of solution, but in terms of the parameters that essentially appear, to having not n, but only n minus k independent dimensionless variables. Which means that when I rewrite this equation in terms of now some new variables, these new variables are called the pi's, which is why this is called the pi theorem, pi 1 through pi p, where p goes from 1 to n minus k. Each one of these dimensionless quantities is a power function of the dimensional quantities. And I'll give you examples of this in a minute. So what does this physically mean? Physically, it simply is saying that whenever I change the units with which I measure quantities, CGS, MKS, whatever, the equation meaning does not change, cannot change. And the meaning of the equation cannot change, and I must have an invariant with respect to dimension. And if I have to have an invariant with respect to dimensions, that means I should be able to rewrite this relationship purely in terms of power functions, because those are the only things which would be invariant with respect to scale, with respect to how you measure things. Okay? So how can we make sense of this? In the context of the Navier-Stokes, the momentum balance equation. I told you every term is essentially a force per unit volume. And if I just count the number of parameters, I am going to now say that the pressure can be written in terms of the velocity and the viscosity and so on. So for a minute, forgetting about P, and I'll do it slightly differently in a minute, then I already told you yesterday, we looked at the fact that you have two intrinsic parameters associated with the fluid, the viscosity and the density, and two extrinsic parameters, the length and the velocity. So I have, if you like, in this very simple context, n is 4, k is 3, because I can write down all these quantities in terms of mass, length, and time. And so I should have just one dimensionless parameter. If I do this, and then one-dimensional parameter will become clear in a minute, if I do this slightly differently, but instead of just counting like Buckingham did, I use the fact that, look, I'm going to use dimensionless variables. So another very important lesson, whenever you write an equation, convert it from dimensional to dimensionless, because you simplify the number of parameters that are there. Then I can rescale time so that t hat is a dimensionless time, defined as the original time times u over L. U hat is a dimensionless velocity, scaled by velocity, and p hat is a dimensionless pressure. And now watch what I've done. I've scaled the pressure by a pressure which I can construct from a viscosity, a velocity, and a length. And again, I want you to remember yesterday how I construct the stress or a pressure in the simplest setting by shearing a plane relative to another. And when I shear it, then I have a characteristic length scale, I have a characteristic viscosity, and I have a characteristic velocity from which I can construct the pressure. That's my dimensionless pressure. So using these variables in that original equation, I can write on a dimensionless equation, and only one parameter remains. And that parameter is this quantity over here, mu over rho UL, and this was first defined by Reynolds and called the Reynolds number, I believe, first by Prandtl, about 20 years later. Reynolds number is the inverse of this quantity, UL over nu, where nu is the viscosity divided by the density. So remember, the viscosity has units of pressure or stress times time. Density has units of a mass per unit volume. The ratio of these two is essentially got the dimensions of diffusion. Okay. What is diffusing? Momentum is diffusing, because what allows one part of the fluid to essentially feel the other is the fact that I have a finite viscosity and allows momentum to diffuse, for example, from a boundary. Okay. A physical interpretation of the Reynolds number, if I rewrite this by just multiplying the numerator and the denominator by another factor of u, is that the numerator corresponds to rho times u squared, so that's a kinetic energy per unit volume, or an inertial stress or a pressure. Rho times u squared is a pressure, and the denominator is a viscous stress. So the Reynolds number is no more than physically the ratio of inertia to viscous forces. So the Reynolds number is large. That means inertia dominates. Makes sense, because the Reynolds number is large, which means this side is large, because the inverse of this quantity multiplied over here, the left side is important. When the Reynolds number is small, inertia is not important. Okay? So we already saw the limits, but now we can essentially take the limits if you want. What happens when not r is either r is equal to 0? So if r is equal to 0, the left side effectively is not important, because 1 over the Reynolds number is what appears on the right side. Okay? So Reynolds number 0 corresponds to not having inertia at all. That's the Stokes equation that I just told you about. And when Reynolds number becomes very large, then this term, these terms, and these terms are both very important. So how do we essentially deal with this? And a particular question of interest is, if Reynolds number becomes very large, you may say, first of all, I've got to redefine the pressure. Okay? Because I can't define the pressure anymore using the viscosity. A way to define it would be to essentially say I'm going to define or rescale the pressure by rho u squared. That's a more natural way to think about it. So the pressure still would remain. This term is a question. Is it important or not? And that's what I want to essentially spend a little bit of time on. But before I actually do something with equations, I want to do something with just dimensional analysis. Okay? Okay. Can we solve problems without essentially solving them? And if you can, more power to you. The answer is sometimes yes, but you've got to be very careful. So you have to always back it up with some other kind of analysis. So first question, there's a typo I think in what I actually gave you in notes. should be rho b for the density of the buoy. So this is a buoy floating on the surface of the ocean. It's quite large. Okay? It's a couple of meters. In fact, there are a ton of these off the East Coast right now, making all kinds of measurements. Now, the buoy is lighter than water. The effective density, anyway, is slightly less than that of water. And if I now try to push it down, there is a resistance. It wants to come back up. And so the simple question that I can ask is, what is the frequency? And I know everybody over here can do that calculation by writing down balance of forces. Okay? But I want you to essentially do the calculation, not do the calculation, and still tell me what is the density, what is the frequency of oscillations of the buoy. You might think it should depend clearly on the relative densities. It should depend on the size. It should depend on the absolute density of one or the other. Because once I have the relative density and the other density, I know both. Depend on the size, and presumably depends also on gravity. Okay? So can we essentially say something about this from dimensional alone? And if I do a count, how many independent quantities do I essentially have? 1, 2 densities, that's 3, 4, 5. Okay? And how many variables, how many dimensions can I essentially write everything in terms of? Mass clearly appears over here in the density, length appears in the length scale over there, and time, of course, appears in gravity. So I have 3 dimensions, 3 quantities, 3 independent dimensions, mass, length, and time, and 5 variables, and I'm trying to relate them. So Buckingham pi theorem tells me that I can write a relationship with just 2 dimensionless quantities. What are those 2? I know it's early in the morning, but it's not that early.
The ratio of the...
Ratio of the densities? Yeah, that's one, obvious. And the other one?
Frequency squared G.
Yep. Speak up.
So it should be something like frequency squared G rho R cubed.
Okay, so what you're saying is that I can write down omega over, there is a natural frequency, it's the frequency of the pendulum of size r, which is square root of g over r. So that's one natural parameter. This has dimensions of 1 over time, that has dimensions of 1 over time. So that's one quantity, one of my pi's. And what is the other pi? The other pi, as people already said, is either delta rho over rho or rho 1 over rho 2. And you can clearly see that there is no reason why you choose to write one over the other. Okay? And so what I can do is I can write down that the relationship is simpler than the original one. The relationship is f of pi 1 times pi 2 is equal to 0 rather than omega is equal to that. Or equivalently, I can write down omega is equal to square root of g over r times a function of rho water over rho buoy. And as far as dimensional analysis goes, that's it. I can't do more. But everybody over here knows more physics than just dimensional analysis. So this is your first homework. Okay? Find out, tell me what you would actually get this functional form to be. I won't tell you. It's simple enough that you can do it. Okay. Second question. Second problem. Oscillations of a drop. This will come up later in the context of a fundamental instability in hydrodynamics, but for now, I'll leave it there. Second question, not on the scale of the human, but on the scale of a small drop. So these are images of a drop oscillating in air. We excited it with an acoustic beam, and the drop starts to oscillate, and the fundamental mode is a prolate-oblate mode. So you start with the sphere, you essentially have a pressure on it, it starts to become oblate, then it squishes down, becomes prolate, and you go back and forth. Okay? Forgetting about dissipation for a minute, so I'm not going to ask you a hard question, which is what is the rate at which the dissipation occurs, what is the time scale over which the velocity vibrations essentially decay. A simpler question is exactly the same that I asked over here. What is the frequency of oscillations of the drop? But now gravity, I'm going to say, is not important. In fact, these experiments were done in a microgravity environment. Somebody essentially took drops into a vomit comet, went into parabolic flight, and then essentially measured the oscillations. Okay? So gravity is not important, because I told you that it's a microgravity environment. So I can again write the frequency. Presumably it's a function of the size, and it's oscillating because it's got some mass, so it's a function of, therefore, the density, also the size, as I said. What's the restoring force? Well, I know that if I give you a drop, then the sphere has the least surface area for a given volume. What's the force that essentially pushes it back into that? It's the surface tension. So I would imagine surface tension is important, and therefore I would expect that the frequency is a function of the surface tension, the density, and the size. Okay? Again, if I think about the independent variables originally, independent physical variables, 1, 2, 3, 4. Again, I have mass, length, and time. So now I have just one, which means I get an answer without actually having to solve an equation. I don't really have to write down the Navier-Stokes or the Euler equations or anything like that. So what's the answer?
Square root of gamma over rho r cube.
Okay. So this is problem 1. So problem 2, omega is the square root of gamma over
Rho r cube.
rho r cubed. Okay? I'm not going to say whether it's right or not because everybody over here can check for yourself, but with dimensions, but let's just get an intuition for should the frequency increase with gamma?
Yes.
Yeah, because gamma is effectively the spring constant. It's telling you how things should recover. Okay? So even if I don't know whether the exponent 1/2 is correct, at least I know that the power, the sign is correct. What about if I increase the density? The frequency should decrease. Well, it's harder to move, more inertia. What about if I increase the size? Same thing. So I've got the signs right. First thing, always, I want to get the sign right, and then only worry about whether I get the magnitude right. Okay? So the signs are correct. I leave it to you now to check that this is in fact correct. And a very interesting thing is look at the dependence on the size. It's very non-trivial. It goes as the -3/2 power. If you had to do a calculation, it's actually not so easy. I mean, it's a few lines, but this is not even a line. Okay, that's the second question. You can check the answer. Third question, which again you're going to actually come to, again, right through this course. I have a polymer or a particle, a colloidal particle, and it's moving around. It's buffeted by thermal energy, collisions associated, it's moving out because of its thermal energy, it's buffeted around by molecules around it, it's got its own thermal energy, it's moving in a viscous bath. I want to now ask, what can I say about the effective diffusivity? Okay. So this relation, first of all, I have no reason to believe that there should be one. In fact, this is one of Einstein's great papers, co-written independently with a Polish scientist, Molikowski, and an Australian physicist, Sutherland, basically all more or less came to the same conclusion slightly more than 100 years ago, which related microscopic properties associated with the fluid, the viscosity, the size of the particles, and the thermal energy with something macroscopic which had been known for a long time, which is that particles move from regions of high concentration to regions of low concentration, or effectively if I start with a blob, the blob starts to diffuse. So that's a macroscopic experiment, a macroscopic observation, and the beautiful, powerful idea was relating that to something microscopic. If there is a relationship, then perhaps you can ask, what is that effective diffusivity? And now I've essentially said something already which is non-trivial, that it's a function of these things. So it's already a very, very subtle question as to whether it should or should not be a function, but I'm telling you that it's a function of thermal energy, the viscosity of the environment, and the size of the particle. And I ask you now, if I use dimensional analysis, again I have mass, length, and time. I've simplified the problem for you because I have 1, 2, 3, 4 quantities, so I should be able to write down just one relationship. Tell me what the relationship is. And you will see this repeatedly, so again I'm going to leave this to you. Okay, you can do the algebra and figure out diffusion constant is length squared over time, that's an energy, that's essentially a force per unit per unit area multiplied by time, and that's the size. Do the gymnastics to figure out what the dependence is. I will do the next couple of calculations. These things are our exercises. Okay? Actually, I'm sure people over here know that, so maybe I'll put it up. And then you can check. Somebody tell me. Okay. Of course, dimensional analysis doesn't actually tell you the constant. Doesn't tell you the constant. I have to emphasize that. Here too, there's a constant which is hidden over here. So that constant can be determined only through an experiment or a real calculation. Okay, you can check that. My fourth example, instead of having a real tsunami, I chose this drawing by Hokusai, where for scale, I mean, I don't know whether this was exaggerated, but presumably it's a context of perspective as well. He's trying to depict Mount Fujiyama over there, and you have this massive wave because he's much closer to the wave than he is Mount Fujiyama. Okay, so in 2004, I think, the day after Christmas, there was a massive earthquake in Indonesia, and almost 100,000 people were killed around the world. Okay? Most of the people who were killed were in the Indonesian islands, almost 50,000, but there were 10,000, 15,000 people killed in Sri Lanka, similar numbers or slightly less in India. The distance between India and Indonesia is a couple thousand kilometers, 1,000 kilometers or so. So you would think that there should have been enough time. So I want to ask you whether there is enough time. Okay. Which is the same question as asking how quickly or how slowly does a tsunami propagate on the surface of the ocean? What's the cause of a tsunami? Well, the cause of a tsunami is an earthquake. What leads to an earthquake? Plates on the surface of our planet, on which you and I are standing right now, move relative to each other. These plates are big, okay? Thousands of kilometers in size, this way. Not so big in the other direction, tens of kilometers thick. What about the ocean? The ocean is also huge lateral dimensions, thousands, but depth is kilometers. So this is an interesting question because it essentially has already a separation of scales built in. You have separation of scales built in the crust itself. You also have a separation of scales built in because the body of water on which this wave is propagating has a massive lateral dimension, has a much, much narrower, much smaller vertical dimension. So the tsunami, if you like to imagine it in your bathtub, is you essentially plunk a piece of metal, a wood, or yourself. As soon as you do that, you get a sloshing wave. So the first question I've got to ask, I want to figure out the time, is what is the speed of such a wave? Okay. So I want to ask the question about the speed, but effectively what really I'm interested in is the time. So I would expect the time should be a function of the distance to where I started the wave and where I'm essentially measuring it, or the disaster area. It depends on gravity, because fundamentally the water wave is moving because you essentially are taking a slab of water and you're just slamming it down, or you're lifting it up and letting it go. It should depend on the wavelength of the wave, presumably, and it should depend on the depth of the water in which it's there. Okay? So I want to break that problem and write down T is equal to U to L over U, where L is the distance and U is the tsunami speed. Okay, so I'm now using a bit of physics. I'm not just going to do dimensional analysis. So the real question is, what is the speed of a tsunami? And the cartoon that I'd like you to have is, even though the wave looks horrendous by the time it comes to shore, it actually looks horrendous because essentially of something very simple, because of conservation of mass. Because no matter how small the amplitude of the wave is, it starts to come ashore, so essentially it's moving up a sloping bottom. If it's moving up a sloping bottom, the bottom surface is essentially exerting friction. The top of the liquid is continuing to move, so the wave starts to overturn and thicken simultaneously. So that's why the wave looks big when you come up close to an obstacle. But I already told you what caused the wave in the first place. It was an earthquake occurring over a slab which is hundreds or thousands of kilometers. So the wavelength of a tsunami, this is the water, This is the coast. The wavelength of the tsunami is actually massive compared to the thickness of the water layer. It's of the order of the scale on which you disturb the liquid, 100 to 1,000 kilometers. So the wavelength, and this is why, if you essentially look at the folklore or read the folklore, the best strategy if you're on the coast is to go in the wrong direction, is to go towards the ocean. Because as you go towards the ocean, you don't feel anything. Because the mass of liquid that's moving is huge, but the size over which it's moving is even huger. Okay? So do the wrong thing. Don't go this way. Go, if you're in the water, move into the water even further. Lambda is huge. And in fact, lambda is much, much larger than h. So there's a lot of arguing with hand waving wildly that I've used so far. Mainly to essentially emphasize that this lambda is so large that all interactions are going to be essentially determined by just the thickness of the water layer itself. In other words, if I essentially disturb the liquid over here, it's not really going to feel things far away, farther than a few times the thickness, because that's the natural scale. So I've given you the answer. So how do I construct a velocity from h and g? So it's the pendulum thing again. It's just square root of gh. Let's do that. H is of the order, at least in that part of the ocean, I have the numbers here, so let's make sure that I have. Yeah, h is of the order of about, the deepest part is about 5 kilometers. G is 10. So V, or U, square root of GH, is of the order of about 200 meters a second. Okay? Distance is of the order of 1,000 kilometers. That's 10 to the 6 meters divided by 10 to the 2. That's 10 to the 4. That's 10,000 seconds. That's a few hours. That's exactly in the right ballpark. It takes about 2 to 3 hours to essentially travel a distance comparable to a distance between continents. So there's plenty of time. The sad thing is that there wasn't a way to communicate this information. And because there wasn't a way to communicate this information, a lot of people unnecessarily lost their lives. But that's all. That's it. That's the basic theory of a tsunami in terms of how long it takes to propagate. Now, there are a lot of details associated with the damage that is done when it runs offshore and so on and so forth, none of which, of course, this very simple-minded picture tells you. But there's a lesson, which you can essentially do a lot with something very simple. Okay. Going on to even larger things.
I have a question.
Yes, please.
Why is it obvious that the estimate does not depend on the amplitude, how much you disturb the plate?
Okay, very good. Yeah. So it does have a dependence weakly on the amplitude, but the linear theory essentially obviously does not. And I'm only telling you about the linear
Why is
theory.
it obvious that this is weak?
It's not. It's initially likely to be weak just because the scale over which I'm deforming the continents is a few meters, but I'm moving the continental plates a scale of a few meters, and the actual lateral extent over which I'm doing this is of the order of hundreds of kilometers. So therefore, I would expect that the amplitude of the wave is relatively small, but the extent over which I'm essentially deforming it is very large. So that's the picture. So essentially the separation of scales again. Question?
Is there a way to estimate dissipation time?
Not in this picture.
Not from scaling.
And you can't do this actually with scaling itself because the viscosity that you should actually have is not a molecular viscosity.
It's not a water viscosity.
It's much higher than
friction,
that.
it's friction.
Bottom friction
Bottom
is
friction.
turbulent, so you have an eddy viscosity because you're generating a lot of vorticity, so the actual dissipation is much larger first. Second, you also have radiation because these are waves on the surface. So some of the energy is essentially taken up by radiation as well. So for both those reasons, accounting for the time is a lot more difficult. In fact, if you actually look at satellite images of how tsunamis propagate, they will essentially rebound multiple times when they reflect off continental shelves. So it's very slow. The amplitude slowly dies down, but not as quickly as you would imagine. Okay, Question?
Could you please explain why the velocity should be proportional to the depth, the h, or actually the square root of h?
No, okay, so I went through this perhaps too quickly. So what I said is h over lambda is much, much smaller than 1. Okay? The wavelength is of the order of hundreds of kilometers or even thousands. The thickness of the water layer is of the order of a few kilometers. So I would expect that the velocity, which is a function of g, h, and lambda, I'm going to write as u is equal to, so constructing a velocity from two of these parameters, the ones that I know are fixed, times a function of h over lambda. That's what I can essentially deduce. Okay? That's just from dimensional analysis, because I want to construct a velocity from this, but I have an additional parameter because, again, if I think about it, I have 1, 2, 3, 4. Buckingham theorem tells me that essentially I have 4 quantities, but I only have 2 variables, which are length and time. Mass is not there anymore. And so I must have 2 variables. One variable is u over square root gh, another variable is h over lambda.
Yeah, I can understand this, but I want a physical reason.
Physical reason. Okay. Physical reason is I just balance kinetic and potential energies.
Okay.
Okay. So kinetic energy is going to be essentially associated with the I'll do a calculation. So if you wait, I will do a calculation in the context of linear stability, where this will appear very naturally. So right now, I just want to do it in terms of dimensional analysis.
Okay.
Okay. Yeah.
When you say, I mean, to get the final number,
Yeah.
you estimate, you could have also rewritten your equation instead of h, you could have written square root of g lambda. Right? That's still good.
Indeed.
And it would be a different function of h over lambda scaling function.
Yes.
But then I guess that doesn't allow you to take lambda goes to infinity limit.
Exactly. Yes. Yeah. And I think that's an important point, and this will come back, I hope, multiple times. I am assuming that this function, f of h over lambda, in the limit h over lambda goes to 0, approaches something sensible. It's a constant. Who said it should be like that? Okay, and there are plenty of phenomena in physics where this is not true. Small does not mean negligible. And I'll show you examples of that in the context of a boundary layer problem. But right now, this is some combination of pure algorithm up to here, and then hope. And hope is the only thing that drives us in science when we don't know an answer. Or we can go back and check eventually, or have experiments. Question?
Well, it's more than hope, because you know that
Yes.
when the limit lambda goes to infinity, you could solve the problem.
Yeah, but that's because you knew something, and I'm saying purely based on this.
Wait, so to get this final answer, 2 to 3 hours, you also were assuming this constant's of order 1?
Indeed, exactly. So as I said, in every one of these problems, I don't know the constant, So there will be factors, and usually when I have frequencies, there will be factors of 2 pi and time periods, and I have to be careful. And you're absolutely right. In lots of problems, you assume that the constant is order 1. And unfortunately, in hydrodynamics, I'm not going to have a chance to really tell you, but there are lots of cases where the constant is not order 1. So the situation when Reynolds number becomes large in a critical value and you get instabilities, it's not 1. For some problems, it's 1,708. For something else, it's 544. And you get that because when you solve the problem, there's nothing you can do about it. Indeed. So this is both fun, but it's also a caution. As I said before, when I started, you can't get all the answers, but you can get something. At least you can simplify the number of parameters on which you essentially expect the answer to depend.
Can I ask a question about that?
Please.
So we always say order 1. He just said order 1, but it doesn't really. It just has to be constant. If it's
That's
not
exactly.
order 1, just change your units.
No, it's a constant which has not got any units. It's a number.
No, right, but
It's a number.
That's
Has,
true, but if it's 1,000, it doesn't make a difference.
it does make a difference if I actually worry about whether the plane will fly or not. So it does matter for some things.
Yeah, but you've got the scaling. It doesn't matter?
It depends on the question. If you're an engineer and you're building something, of course it matters. If you're interested in understanding the
We're not
phenomenon,
going to build things doing this, right?
2 to 3 hours.
I-
Yeah, I mean, if you want to know, does it take 2 hours or does it take
Take 1 minute.
hours, then 1,000
Yeah.
matters.
2 hours or 1,000?
Well, if your question was how long does it take for the wave to get to the shore, and if the difference between 2 hours or 2,000 hours, then that factor of 1,000 really doesn't matter.
I think we should continue. Dimensional analysis, everybody loves it, and simultaneously everybody hates it. For exactly the same reasons. Okay, so there's plenty of time to discuss this over the next 4 weeks, because you'll see a lot of this. But I want to charge on, okay? Because it can become very philosophical very quickly. Okay, one more example. The yield of an atomic explosion, the first one of its kind, from which this picture was taken, was 1945, around this time, July, not so far from here, in New Mexico, in Alamogordo. And this is an image, I think, of that, or a slightly later shot, taken about 6 milliseconds later. Okay, so you can probably make out some things which are about to be obliterated in the background. So this is a fireball, which is of the order of 100 or so meters. As I said, taken about 6 milliseconds later. And the question is, what is the yield? And during the war, as I'm sure most of you know, there were multiple attempts on multiple continents to essentially build an atomic weapon. And when this first one was exploded, a very important part of the secret was, what is the yield? You know, what can I destroy? How many people, sadly, can I essentially destroy with this? And 3 people, more or less simultaneously, did a calculation. Sadov in the then Soviet Union, John von Neumann, who was here, and G.I. Taylor in the UK. More or less at the same time, did a calculation. They were all classified documents, eventually published. G.I. Taylor was the only one who actually also made a connection to the data. And he made the connection to the data through a remarkable accident. On the cover of Life magazine, a few years later, I can't remember the year, but 1950 or so, a photographer published a sequence of these fireball images. And foolishly, so first thing is you can get an estimate of the length scale because you have some objects in the background which you may be able to recognize. But foolishly, or at least he didn't think that it was foolish, and obviously nobody else thought it was foolish, he also put the times. Okay. 2 milliseconds, 5 milliseconds, 10 milliseconds, and so on and so forth. And Taylor calculated the constant. Everybody's been asking me about this constant. Taylor calculated the constant in 2 ways. He actually did a calculation, which I won't do for you, using gas dynamics, but he also just plotted the data cleverly. Got the constant and got the yield. All right. Now in this case, the constant turns out to be, so first question is, how do I relate the energy to some parameters? Or equivalently, I could turn this around. I could ask, what is the radius as a function of time? Presumably the radius as a function of time starts out the size of maybe this table over here. It was 2 or 3 tons, diameter about a meter, length a couple of meters. It exploded, so the radius increased as a function of time. Question, how does the radius increase as a function of time? Presumably it depends on the energy, the initial energy. So I've turned that question around and written down the question as, ask what is the energy as a function of the radius, time, and the density of the gas in the fireball, if you will, the density of air, more or less. Okay, so actually we can do this if you've not already done it by now. So I have 1, 2, 3, 4, so I should be able to write down just a single constant. Single function, which relates to 2. In fact, I'll do this maybe using very cavalier physics. So I'm going to say the energy, which was all associated with uranium, is essentially now converted to kinetic energy, converted to temperature, and so on. At the simplest level, if I think about just the kinetic energy, I would say it's the mass of the fireball, assuming that the radiation that's actually also propagated is a fraction of it, so it's comparable. Mass times, density times the size cube times v squared. Okay. Extremely dumb estimate. And so I basically also write V squared as R dot squared. And when I write down V squared as R dot squared, I would say that just at the level of dimensions, this goes as rho R to the 5 over T squared. I'll make this an equal to sign. I'll put a constant in front of this, and there you go. Okay? So that would say that R goes as E over rho to the power 1/5 times T to the 2/5. Taylor plotted the photographs that the Life magazine photographer gave him, or gave the world, and calculated the only thing which was missing. He first showed that the power law works, and then he actually calculated C. And once you have C, now this is an equation, it's not just a scaling law. And in this particular
C
problem,
independently somehow?
hmm?
You got C independently somehow?
He got C, yes, he also did a gas dynamic calculation, separately, yeah. But this is, I'm talking about just analyzing the experiment. And it turns out over here, C turns out to be, I think, something like 1.08.
How did you know E?
That's the definition.
That's the question.
See that every.
Okay, so there were two unknowns, C and E. That's what Leo's question was. How did he essentially do a separate calculation? So he actually had to do something independently. And he did a gas dynamic calculation. And so you have also an estimate for C, but you still don't know E. And now you essentially get E from both. Okay? What is E? So turns out to be, using an estimate, E turns out to be the order of 10 kilotons of TNT. I'll just give you the number, okay? And the actual yield is about 20. So it's fabulous, given all the complexity of such a hard problem, that you can get so far without really doing a calculation, but without doing a full calculation. Although that's not completely true, because you had to do a calculation if I wanted to get E. If I wanted to get the scaling, even I don't care about that.
So what did you say, what was the answer and what was the rest? What was the...
Factor of 2. It's the first atomic weapons had a yield of the order of about 10 kilotons of TNT. So TNT, trinitrotoluene, I should tell you, has, when it explodes, exothermic, so its typical energy production rate, or energy production is typically for 1 gram of TNT, you will get 1 kilojoule. Compare that with essentially the amount that it takes to heat a gram of water by 1 degree. 1 gram of water, 1 degree will give you 1 joule. So this is 1,000 times more energetic. TNT is, if you want to compare things. And you can put in the numbers with R of the order of 100 meters, and you get something of the order of about 10 kilotons. Okay. Last problem, because this will essentially now move us towards actually doing something, starting from the Navier-Stokes, rather than waving your hands, my hands, rather than my waving hands, and then hopefully convincing you, but maybe not, is a lot of the problems associated with hydrodynamics were motivated and inspired by trying to understand how to move through our fluid environment, either in water or through the air. And so a basic question had always been trying to understand how to calculate the drag on a body. And this plot is not visible, and there's a reason it's not visible, because I don't want you to pay too much attention to it. Okay? But I'll just tell you what it's supposed to indicate. It's indicating over here something called the coefficient of drag, which I'll define in a minute, as a function of the Reynolds number. And the Reynolds number is essentially changing from of the order of 10 to the order of 10 to the 8. And I defined the Reynolds number for you. I should do this again, because I want to essentially give you some handle on it. I should have done that before. Reynolds number is UL over nu, so this is a good opportunity for me to do this. Mu is mu over rho, and for water, this then turns out to be 10 to the minus 3 meters squared per second. Okay? So I want to compare Reynolds numbers for you and then ask about what this actually means. So the Reynolds number for a bacterium moving at a velocity of a micron per second, of the order of a micron per second, so that's 10 to the minus 6. For the velocity, micron size bacteria, 10 to the minus 12, divided by 10 to the minus 3. So the Reynolds number for bacteria is of the order of 10 to the minus 9. Okay? That means that inertia is essentially unimportant. That's one limit, and we'll come to this in some detail. So Reynolds number is small means that, remember, the Reynolds number is the ratio of inertial forces to viscous forces. So Reynolds number is small basically means inertia is unimportant. If inertia is unimportant, then I live in an Archimedean world. In a world where what Archimedes used to think was the force is proportional to the velocity, not the acceleration. So I live in a world where acceleration, inertia is not important, and the force is proportional to the velocity. And you might think that we have good intuition for that, because after all, that was the first attempt at, in a pre-Newtonian world, trying to relate geometry, which is changes in position, to forces or notional forces. But in fact, intuition for us in that regime is very bad. And that's because we live in a very different world. So if I essentially substitute, instead of u is a micron per second, u is a meter per second for you and me, or 10 meters per second, as some people can essentially run, and we'll find out in a few weeks. The size also a meter. Okay? So if I run at 10 meters a second, and I have a size of the order of a meter, then the Reynolds number becomes...
What's new for air?
Ah, thank you. So I said that last time. So nu for air is of the order of 10 to the minus 5 meters squared per second. Mu and nu are same numerically because density of air is approximately 1 kilogram per meter cube. So Reynolds number for a human is of the order of 1 or 10 meters squared, 10 meters per second for Usain Bolt, times 1 meter, actually it's 2 meters, okay, divided by 10 to the minus 5, and so this is 10 to the 6. Okay? Very large Reynolds number when you go from the bacteria to the human, both because the velocity has gone up, the fluid has changed, and the size has changed. All three things have changed by large orders of magnitude. And this is well known. If you're a biker or you're a runner, as you start running, you essentially start to really feel the influence. Okay? A blue whale, well, you can calculate. Okay. The size is larger, the viscosity is smaller, the speed is, of course, much less, by a factor of 10, or it's not much less. It's slightly more, it's a factor of about 2 more, so 10 to the 8 or so. Okay, so a fundamental question in all these situations is, what is the force as a function of all these parameters? The size of the body, the density of the liquid through which I am moving, the velocity with which I am moving, and the viscosity of the environment. Okay? So that's a fundamental question which has absorbed people in hydrodynamics for 100 years and presumably will continue to absorb people for a lot longer than just the first 100 years, because there are lots of interesting problems where this is the only parameter that appears. So F is a function of rho, u, mu, and r. And again, I have 1, 2, 3, 4, 5. So the best that I can do is to reduce it to just 2 parameters. And there are many ways of writing this. One way to do this is to say F is a pressure. This was the way Newton thought about the problem. He thought that as the body moves through the air, molecules essentially impinge on me and they bounce off. And so as soon as I have a change in momentum associated with change in direction, I generate a pressure. And if I essentially have elastic collisions, then I have a momentum reversal, so that generates a pressure, which is essentially just the density multiplied by u squared, multiplied by the area that I essentially project. So that's F over rho u r squared, rho u squared r squared is a parameter which has dimensions of the force times some function, and that function, what do you think? I'm deliberately going to write it as using these to construct another parameter, which is the Reynolds number. Now that's not the only way to do it, but this is the way now people do it, because there is a physical meaning for this quantity, the ratio of inertia to viscous forces, and if you like, then the other parameter. So this is pi 1, and this is, if you like, pi 2. Well, that's the best that you can do from dimensional analysis. The rest, 100 years later, we're still studying it. Okay? Very hard problem, because you have all kinds of transitions as you change this parameter when I talk about what happens in the fluid with a body moving through. And I'll tell you tiny little bit about it in the next 15, 20 minutes. But this is the best that you can do based on dimensional analysis. Okay, so what I want to now tell you is that that graph actually...
That guy goes linearly with,
Speak up.
well, let's say small RE goes linearly with RE.
That's what we expect, exactly. And then at large RE, this is the fundamental question. Does it depend on RE? As RE goes to infinity, Newton's idea was F is equal to just some constant times rho u squared r squared. Is that true? And I'm going to tell you that's only part of the picture, because that's associated with the drag induced by pressure. But there is another kind of drag, which I'll do a calculation for, which is associated with the fact that as the fluid moves past the body, the fluid is stuck to the body, and so there is a drag which is called skin drag, which is a very different notion. In one case, it's associated with the isotropic part. Okay, remember when we talked about the stress, I have an isotropic part and an anisotropic part. The isotropic part is the pressure, and the anisotropic part is the shear. And just associated with fluid moving past skin means that the fluid is stuck to the body and not stuck far away. So there is an additional contribution, because the fluid is decelerated, that means it's essentially a force in the body. Okay, so this quantity, F over rho u squared, r squared is called the coefficient of drag. And what's really plotted over there is the coefficient of drag as a function of Reynolds number. And it's a very non-trivial function. Okay. So what's not plotted is what Leo was asking, that at small Reynolds number there is an increase. This is actually well beyond that. Okay.
That's function G.
Hmm?
That's G.
That's G, effectively. Yeah.
What kind of number is the maximum?
It depends on the body. For a sphere, it's of the order 10 to the 3. Okay, and so this again comes back to this question, oh my goodness, I thought that the critical Reynolds numbers and the critical numbers in front of all these is 1. It's not. In hydrodynamics, unfortunately, it's almost never 1. Because if you thought that the transition from when inertia was important to when inertia is not important should be associated with Reynolds numbers switching from less than 1 to greater than 1, you're wrong. It's typically of the order of 1,000. But it depends. I'm saying that in some situations at the order of 40 for a cylinder, and if I ask what happens when I have a cylinder in a flow, and I ask when does vortex shedding occur, in a particular instance, I can't remember the details, it's the order of 100. But it's very, very, I've never seen a problem where it's 1.
But are you saying it's rather than, so it rises linearly at small Reynolds number, and then rather than plateauing, it goes down, not amount of time?
Yeah. Yeah, and this is a very long story, and it's associated with the fact that, in fact, this is all done for a sphere. I said it's a body, but it's actually a sphere. And let me give you an intuition for this, because what's really happening is that on the surface of the sphere, which is convex, it's fairly well behaved. But what's happening on the rear is very tricky, because what's happening in the rear is that you might imagine that you should essentially just leave, the fluid just leaves the sphere. Okay? So what you have is effectively a pressure gradient which is opposing the flow. And when you oppose the flow, all kinds of things can happen. You can get instabilities, you can get shedding. And so what happens is in the laminar regime, that zone where the fluid leaves is much further than what actually happens in the turbulent regime. So you actually have less drag in the turbulent regime. That's why golf balls, for example, have dimples. Because they want to decrease the transition. Decrease the transition, decrease the transition to turbulent, because once you get into turbulent, the drag on this is less. This can be, it's a semester worth of hydrodynamics, and that's all I want to really say about it. Okay? But I want to do a calculation. Now, I already told you that, in fact, so I already wrote down what I just told you on the board, that I can write down only a function. I want to now ask, how can you make sense of this? And I want to do this using a toy example. It's a toy example which you will laugh at me for, and I hope you do, because it's something which you can solve exactly. Because I want to indicate a way of calculating by approximation rather than using analysis. Okay? So, what happens? So the fundamental question is, what happens as Reynolds number tends to infinity? It's not equal to infinity. What is the limit? That means I want the dependence on Reynolds number. So here's a toy example which makes the point in a very simple way with a simple equation. So I have a damped spring to which I essentially have a force, a constant force that I apply, and I initially start out with the spring being unextended. And everybody over here knows how to solve the problem, can solve it with exponentials. But in fact, what I want to actually do is tell you, which I'm sure you've noticed, you know this again from elementary mechanics, that there is a natural time scale of the problem. The natural time scale of the problem is the ratio of the damping to the spring stiffness. So if I rewrite this equation just by dividing, not having scale things, I'm not going to scale time yet by tau, I just read it in that way, dividing everything, I have this equation, and instead of solving this, I'm going to look at times which are small compared to tau and times which are large compared to tau. Okay? If the time is small compared to tau, so I'm essentially at the very beginning, this term, because that's the velocity, is not small. If that's not small, in particular this term, because t is, so there are two t's, it's a time t, and there's a natural time scale. And I want two limits, maybe I think I have it on the next, okay. Yeah, I do. I have two limits. One is when t is less than tau, much less than tau, in which case this term is not important because the velocity is going to be dominant, in which case I just balance these two, and if I balance these two, I get that x increases linearly. No surprises. And then when time becomes large, then this term is not important because I expect a balance potentially between these two. And again, I can self-consistently check everything, okay? So I make a guess and then I check. That's the way you solve problems where you have to approximate, because you have some intuition, some physical intuition, some experiments which suggest things that all terms are not equal. In this equation I have three terms, and I essentially am always balancing just two. In the Navier-Stokes, I have these two terms which go together really, so 1, 2, and 3. So again, I can ask the same kind of question. Which terms are balancing which ones at different regimes, in different time, in different space? So here in this very stupid problem, I have two zones, two regimes, time much less and time much greater. The time much greater, I reach the equilibrium. Now, of course, you know that the actual solution, which I won't write down, is x as a function of time, looks like this. And what I've done is, I've got this bit, and I've got this bit, with no calculation, really. Okay? The advantage of that is, of course, that if I had replaced this x by some nonlinear spring, I would still be able to solve the problem, because I can still pick up the linear behavior. Of course, over here, I'm going to get something else. But that requires that the term with the highest derivative appear linearly. And that's a very, very basic problem. It's also one which we have often in physics. So in a mathematical context, this is a singular differential equation. It's a singular differential equation because if my natural time scale was very small, that means I would essentially have something which is rapidly increasing and then equilibrate. So if I essentially put tau to this, and I rescale everything so that tau becomes a very small number, you might think I can just drop it. But you can't. And you can't Because if you drop it, you have a problem. You can't satisfy an initial condition. You can't satisfy the fact that x of 0 is 0. Because I've suddenly lost the derivative, and instead of having a differential equation, I have an algebraic equation. K times x is equal to f. Well, what do? I can't solve the initial value problem. So which means now I have an initial layer, a small time, or small or large depending on the value of tau, a time where I can never forget what happens. And then, and only then do I go to the steady state where I don't really care. Because after all, if I started here, I'll get there. If I started there, I'll also get there. Okay? I'm going to give this as a homework. If you can do it, you should, with the help of the TA. But I'm again sure that this will be covered multiple times in many of the lectures that you will see later, where instead of having an overdamped case, you have actually a case, instead of having one with a spring, and no mass, you have a case where you don't have a spring but a mass, and it's driven by noise, and this is the famous Langevin equation, where the forcing has mean 0, but essentially it has a variance which is non-zero. Okay? And again over here, what's the question? The question is, what does the particle do? And the naive picture that you should have is that the particle runs for a while because it remembers where it started, because it has inertia, and then it starts to forget. Then it gets another kick, then it runs for a while, and then starts to forget. So there is a memory, and the memory is associated with inertia. How do we understand that? We use the fact that this term, even if it's present, is not anything. That's what essentially gives it its ballistic trajectory for a while before it runs away. I won't do this problem. But instead, what I want to do is solve problems associated with Navier-Stokes using this very simple idea of the fact that all terms in an equation are not necessarily always important simultaneously. If they were, you can't do very much. And that's a situation where you start switching to something like a numerical method to understand how to patch together things. So I understand this region, I understand that region, I want to patch them together. So just like in politics, it helps to divide if you want to conquer. Okay, so in space, instead of having an initial layer, you have boundary layers. The first ideas of boundary layers actually in fluid dynamics are associated with Prandtl, but in a dynamical context, but there are precedents way before, almost 100 years before, starting with Laplace, and then in between Laplace and Prandtl, Stokes, Rayleigh, Lamb, and so on and so forth. What I want to do is to indicate for you again, using a scaling approach, the solution of two problems, and your TA, I hope, will essentially allow and help you solve the problem mathematically. I'll set up the problem, but I won't actually tell you the actual algebra. There is a little bit of algebra. I want to tell you about two problems which I think are very natural in the context of a lot of problems in soft matter, and they are called Stokes problems 1 and Stokes problems 2. Okay? Let me explain those problems to you. They are both dynamical problems, but they also involve space. First problem. You have a wall, you have a fluid, you have an infinite wall and infinite or a semi-infinite fluid. You suddenly move the wall. Okay? So at time t equal to 0, you have a heaviside velocity. So before t equal to 0, it's 0. At time t equal to 0, you switch on the velocity off the wall, and then you keep it constant. And the question is, what happens to the fluid? What happens in the interior? That's the first question. Stokes' first problem. The second problem is you have the same wall, but now, instead of having a sudden jump in the velocity, you suddenly move it, you oscillate it. Okay? Now, of course, if you oscillate it, you've also got to start from 0. But I'm not interested in the transient. You could be interested in the transient. I'm interested in the steady state. Okay? Or the oscillatory state, whatever it is. Because now I have an oscillating boundary, and I want to know what happens in the interior. Both these problems, I'm sure you will see multiple times through the course in the context of specific applications, but this is an abstraction in the purely hydrodynamic setting. Problem 1, two-dimensional, to keep things simple. You can do it in 3 dimensions. It doesn't really change anything because nothing happens in the 3rd dimension. You, on the boundary is y equals to 0. For all x is velocity that I prescribe multiplied by a heaviside function. Problem number 2 is, instead of having a heaviside function, I have an oscillatory function. And the question is, what happens in the interior? You can solve it using scaling, actually solve it. You can get an idea of what's happening using scaling. You can also do it analytically. I'll tell you about the scaling approach. I will set up the analytical problem, and then I'll let you do the algebra. Okay? So, how do we do this? I have a suddenly moving boundary. The fluid far away presumably has had not any chance to essentially respond. So the fluid far away is at rest. The fluid on the wall, because of no slip, is essentially starting to move. It's moving with velocity u here. So the real question is, what is the scale of influence? What is the zone of influence? Okay? What is this length scale? So, first remark is I told you that in fluid problems you typically have a characteristic velocity scale or a pressure and a length scale. Do we have a length scale here? We don't, because it's infinite in this direction, it's infinite in that direction. So a length scale doesn't exist. But I do have a velocity scale. And I want to keep that in mind.
The plate is not, there's no finite extent of, it's not a plate. You're not moving a plate.
Sorry?
You're not moving a plate.
I'm moving I'm moving the
Whole thing.
whole thing. I'm not moving a finite extent. The finite extent will have all kinds of complications associated with the ends. Far away from the ends, what I'm going to tell you is going to be similar. Okay? I have velocity, and a question for you is should or should it not appear in your thinking? And I want to ask, what is the length scale? So potentially, I have velocity, and of course I have mu, and I have rho. There are no free boundaries. Can I construct a length scale from mu rho and maybe L? Okay? Okay, so I'm going to now posit that there is no dependence on u, and the reason I'm going to say that is because if I essentially change the magnitude, I should expect everything to just rescale in magnitude, but the actual zone size should not change. That's an assumption which I have to back up with the calculation eventually. I'm thinking about diffusion of velocity, because velocity initially starts out 0, at time equal to 0 it's finite, so the velocity is gradually percolating in. How should it percolate in? Well, it should percolate in by thinking about the diffusion of momentum, because I basically am using the fluid layer here to drive the fluid layer there, and there, and there, and so on, further and further inwards as time progresses. So, and this quantity has dimensions of diffusion, and its physical interpretation is the diffusion of momentum. So I know how to construct a length scale using not diffusion, but momentum diffusion. L is the square root of mu times t. Okay? So that suggests that because there is no external scale, the problem is essentially self-similar. Self-similar because all the length scales are coming from the dynamics itself. And everybody over here I know has learned how to solve a diffusion equation. In fact, I'm going to show you that actually the diffusion equation comes out of exactly this problem, and I'll do it right now. Because I want to now go back to the 2D problem, which I've written down over here. Conservation of mass, conservation of momentum in the x direction, conservation in the y direction. So there is no variance in x, because every location at x remains exactly the same. Right? There's no reason to expect any dependence on x, because it's an infinite half space, it's moving. But I expect variations in y. Okay? So if I look at this equation, u can't have a dependence on x, so that goes away. dv dy must be 0, but if dv dy is equal to 0, then v is a constant in y, but v is equal to 0 initially, and so it's 0 for all time. So the velocity in the vertical direction is not there at all, which means that if I look at the second equation, all terms vanish. There are no pressure gradients in the y direction, and everything else vanishes. V is identically 0. Okay? That makes sense, because essentially I have a problem where I'm diffusing horizontal momentum, horizontal velocity upward. There is nothing happening in the vertical direction at all. So I can drop one equation. What happens if I look at the first equation? Okay. So if I'm thinking about the linear regime, I may have a pressure gradient. I'm going to drop the nonlinear bits. Okay. I have to keep this bit, and I have to keep this bit because that's the only way I can build an inertia associated with the fact of initially moving it. What about ux, x, and uy? Well, nothing varies in x. Do I have pressure gradients in x? The answer is no, because I have no mean flow. So this term is also 0, and so I get ut is equal to mu times uyy. Okay? So that suggests that in fact, for the diffusion of momentum, no surprises, mathematically also, I get a diffusion equation with a boundary condition, which is that u of y equal to 0. And of course, u vanishes at infinity. Okay. I have to have two boundary conditions because I have uyy. Okay. You know how to solve the problem, so I'm going to let you do it. The second problem.
Yeah,
please.
so what happens in the limit of, if you want to talk about, of an inviscid liquid?
Thank you. I was going to come back to that in a different context, in a steady problem. The unsteady problem is very hard. But so thanks for asking that. So the question was, what happens if I have an inviscid liquid? Well, if I have an inviscid liquid, I have no way to advect momentum from a boundary.
But if the boundary is rough?
I can generate pressure, but I still have no way of getting shear. So what I'm going to get are going to be flows associated with pressure variations, but not flows associated with variations in shear. So no vorticity, but still I can get flow. Okay? And then you can ask, and I will come to this maybe either, I think I have enough time. I will come to the question of what happens in the steady state as I start to reduce the effect of viscosity, so getting into higher and higher, so I can't drop the nonlinearity, but I won't do the full problem, the unsteady problem, I'll do the steady state. So I did this unsteady case in the linear, and I'll do the steady case in the nonlinear. I'm passing them together is more than I want to, more than I have time. It's been done. Okay? Second problem, second Stokes problem, is what happens if I have an oscillating boundary layer? Sorry, oscillating boundary, not a boundary layer. Oscillating at a frequency omega. Again, for the same reasons, so I'm thinking about a linear problem, I can pull the u out, I don't really care, but I'm now asking what is the zone of influence. And now, because I have oscillations, I won't expect to essentially feel things very far away. I will expect to feel things in a zone close to the wall, because that's where I'm driving it. So how do I construct the length scale from the diffusion of momentum and the frequency? Well, instead of t, I just replace t by 1 over omega. And this length scale is called the Stokes length. And it's a very, very important length in any problem on the small scale where I'm not steady. Because it's telling you if I have different bits of a polymer or a colloid or a gel or whatever it is which are moving, how far into the fluid do they make their influence felt? Okay? As the frequency becomes higher and higher, that length scale becomes smaller and smaller. Makes sense, because I just don't have enough time to essentially push things into the interior. And as the viscosity becomes smaller and smaller, the length scale becomes smaller and smaller. And in the limit, when the viscosity goes to 0, that length goes to 0. Okay? How do I do this more carefully? Well, I indicated it for you over there. In both cases, the equations are exactly the same. The equation is just one. It's a diffusion equation. But in one case, I have a boundary condition, which is the Heaviside function. In the other case, I have an oscillating condition. You can use similarity variables. The similarity variable is, so I look for a solution u of y t is some function of t multiplied by some other function of y over the square root of mu t. And the reason I write it in this form is that y and square root of mu t cannot appear separately. They must always appear together because the only length scale of the problem has to be a dynamic scale. Okay? And then I substitute this into the differential equation, and I can essentially then solve for A and solve for phi using the information that I have. And I have, in the other case, for the steady, or sorry, the oscillatory situation, I just substitute in the oscillating function with a phase multiplied by a function of time, and then just evaluate. Okay, so that's the easy problem, because those are both linear problems. In the last 10 minutes, I want to actually tell you about a harder problem, which is the one that was somehow related to what Phil's question was, which is what happens now, forgetting time for a minute, in the steady situation where I flow past a plate, but now it's not an infinite plate, it's a semi-infinite plate. And the reason for that is there is an infinite plate and I have steady flow, then I really don't know what's driving it and what's happening. So I say that I have now a half space, so I'm not going to worry about anything that happens in the fluid over here, or if you like, I have an infinitely thin plate, so I don't have to worry about anything over here. And with an infinitely thin plate, I have a symmetric zone in the left on below. So I have flow which is uniform, could be driven by a pressure, could be just a pressure, a velocity which is prescribed. It comes in contact with the plate, and on the plate, the fluid comes to rest because I have the boundary condition which says velocity is equal to 0 on the boundary. What happens if it's not 0? Well, that's again still currently being debated in very beautiful examples. For example, I think about birds and I think about feathers. Feathers are not perfectly flat, they are porous. You can have flow through them, you can have flow which starts and stops. How does it all work? We don't know. Fundamentally, we don't know. Neither do the birds. It's up to you to find out. Okay, so forgetting all those things, assuming that the fluid is at rest on this infinitely thin plate, and I'm now asking at steady state, so I don't talk about the startup problem. What happens if I start the flow? I assume that I've had enough time to reach steady state. What can I say about the original question, which is the drag? I solved these two problems at the beginning, plus I understand what's happening in the fluid, but now I want to come back and ask, what is the drag on this plate? In the limit, particularly, of the Reynolds number going to infinity. Because now the pressure drag is essentially 0, because it's not essentially impinging on the solid directly. The solid is just an infinitely thin plate. In the limit, when the viscosity is 0, not in the limit, but when the viscosity is exactly equal to 0, there is a paradox. It's called the D'Alembert paradox, which says that the drag and the lift and all forces essentially go to 0 for a finite body. And in fact, it's not only true for this thin plate, it's true for any shape. And in 2D, the proof for that, which again I won't go into, is associated with the fact that I can map any shape onto a cylinder using conformal transformations, and then I can solve the problem for a cylinder, and then I solve it for all. And if you do that, you find you can't get forces, which was an embarrassment until Prandtl came along and said that even though the Reynolds number is large, which means even though the viscosity is not 0, it's very small, even though it's almost 0, its effect is profound. And it's exactly like that initial value problem. Because as soon as the velocity goes to 0, on the boundary, the fluid has the ability to stick. If the velocity is not 0, there is no resistance whatsoever, so I'll just have a flat flow. So how do I solve this problem? So Prandtl's profound idea was to make an assumption and then check. Make a guess and then check. And his guess was, in the limit of high Reynolds number, or equivalently large velocity or small viscosity, then he said, let me assume that the effect of the wall is limited to a small neighborhood. Of course, he knew what Stokes had done, but that was a linear problem. He said, maybe it's still true for the nonlinear problem. He assumed that, and then further he said that if it is an infinite plate, there is no length scale again. It's a semi-infinite plate, but a semi-infinite plate also doesn't have a length scale. Okay? So that zone of influence where this solid is influencing the fluid is different here than there, but all these sections should be somehow related to each other because there is no length scale. I have to construct length scales now from not time, but from the velocity in the far field, and maybe this length, and use that to construct the other length, because that's the only length scale in the problem. Okay? So what did he do? So the assumption that the depth into which, the depth in the fluid where the influence is small compared to that, if I look at the continuity equation, divergence of u equal to 0, I write down, so just with my notation, so this is the profile, this is location x from the free end, this is delta, this is u, and that's v. My continuity equation is du dx plus dv dy is equal to 0, just counting how each one of these, looking at how each one of these terms varies. Du dx looks like u over x, dv dy looks like u over delta because it's minus sign. And if I say that delta is much less than x, this quantity is much less than x, that would suggest that the vertical velocity is much less than horizontal velocity, which makes sense because I'm not perturbing it a lot in the vertical direction, I am perturbing it in the horizontal direction. That's an assumption. Okay, you've got to go back and check. So Prandtl's assumption was that. And then he looked at the steady state. So he didn't look at the development of the flow, he dropped this term, time-dependent term, and then he looked at these equations and then said, this term is important, this term and this term scale the same way, because over here I have a du dx, over here I have a v and a y. Okay, so v over y is the same as u over x because of continuity, so these two terms look similar to each other. I could have a pressure gradient, but I don't have a pressure gradient, so I'll maybe keep that. And then of these two terms, of the viscous drag, I have a uxx and a uyy, which is larger. Speak up. Uyy, because y is small, so the gradients in the vertical direction are much larger than the gradients in the horizontal direction. So that term is also small. And so Prandtl said, there are three terms. I'm going to assume that all three terms are of the same order. Okay? You can have a situation where the pressure gradient is in one direction, where the pressure gradient in the opposite direction, and the pressure gradient is 0. He actually did the general case, and then Blashes came along and said, I'm going to think of the simplest situation where I'm going to drop effectively the pressure gradient, so I have nothing over there. But effectively, I've written down now those two terms. The rho times uxx, which looks like rho u squared over x. These two terms will be exactly the same because of continuity, because of that balance. And on the right side, I have only mu times uyy, which is mu times u over delta squared, which is the same order as d over x. And now something nice happens. I get an expression for delta in terms of x, which is exactly what I said. So all these cross sections are essentially just mirrors of each other, but rescaled. Okay. So delta is mu x over u to the 1/2, and it's worth rewriting. I can pull the x out, divide on the left side, so I get delta over x, and then I get, instead of mu x over u, I get mu over ux. But the Reynolds number is ul over nu, which means that the right side is the Reynolds number to the power -1/2, but using the length scale x, because that's the only length scale that I have. Okay? And I'll give you a physical explanation for that in a minute. Actually, I have to tell you the limit. So delta over x goes as the Reynolds number to the power -1/2, so that when the Reynolds number becomes larger and larger, indeed, delta over x is small compared to 1. So Prandtl's assumption leads to a result which is self-consistent with the assumption. So this is the possibility. I should emphasize this is a possibility. It is not the possibility. These are nonlinear equations. They have multiple solutions. And again, there's a huge amount of work that's gone on to try and understanding what happens. But this is one possible scenario. So delta over x is known as a function of Reynolds number, and now I can calculate the drag, which is what my original goal was. The original goal was to calculate the drag, so I first want to calculate the stress on the boundary. The stress on the boundary is the velocity gradient, because the fluid is stuck on the wall. Far away it goes to the bare velocity. So I have to ask, how quickly does the fluid velocity go from 0 to its maximum? And it goes from 0 to its maximum over a scale which is delta. So the shear stress at any location is mu times du dy, which is mu u over delta in terms of scaling, which I can rewrite like this, because the delta already has a u over there, 1 over delta, therefore to give me another u, putting it into the bracket, I get rho mu u cubed over x. And again, there's something interesting physically. As x becomes larger, the stress becomes smaller. What's the intuition? Because there is much more length over which I can distribute the gradient. Okay? So the wall shear stress decreases as I go further and further. It's very high, in fact, it's actually singular there. Because as x goes to 0, you get a singularity, 1 over x squared root of x. But that's an integrable singularity, so you don't have to worry about it. Because what matters is the force, not the stress. Okay? So the total drag now on a long plate would be the integral of this, forgetting about end effects for a minute, and you now get the dependence. If I integrate this, I'm going to get rho mu u cubed L to the 1/2, and notice the dependence, which is already present over there. It's u to the 3/2. In the linear regime, it was to the power u. Newton's calculation was u squared, and now you have u to the 3/2. Okay? So in fact, and this is probably a good time for me to stop, so comparison I just told you, you have different bits. You can do a much more careful analysis than I have done, and when you do this, you will get the correct prefactors.
So this is the point where this kind of stupid u equals 0 boundary condition
It's just
comes in.
deadly.
Yeah, so the issue is, what can you say about that? Because that's sort of there's no physical reason for that.
Indeed. Okay.
Yeah.
So as you now move away from that, you've got to revisit the problem.
That's what I'm.
And what can and what does happen is then you get actually much lower drag, effectively, because you're allowing for slip. Now the details of how that happens, people have argued about and continue to argue. For example, if I have a hydrophobic surface, or if I have a rough surface, what happens? I already told you, with the rough hydrophobic surfaces, people are still arguing about it. With the rough surface, what's known is that you essentially can reduce the drag. You have a completely different regime. So this assumes laminar flow.
Yeah.
Once I have roughness, and I can have turbulence, I have vortices, all hell breaks loose. There is a beautiful, another similarity hypothesis made 40 years or 30 years after Prandtl by von Karman, which he said that in fact whatever I have over here is, and now he's thinking about the infinite plate, not even the startup, so there is no scale at all. So he said I must have a similarity situation again, and he basically came up with what's called the log law of the wall. So the velocity decays logarithmically away from the wall, or increases logarithmically away from the wall. People have argued recently about that it's actually not really a logarithm, because if you look at the experiments carefully, you can actually have a dependence on the Reynolds number, but there is a logarithm on the Reynolds number and a Reynolds number, and I'm not really, I don't know enough. But it's very much active. And your question about what happens if I have change the no slip condition, what happens if I have suction, what happens if I have blowing? And by the way, modern airplanes, all the planes that you essentially probably flew on, use all kinds of complicated tricks at the leading edge or just behind the leading edge of the wing in order to try and push the region where the flow separates in order to try and beat this. Because this is fundamentally why you have such a difficult time with respect to moving through the air. Well, this is one part, there is separation. When I say this is I'm lumping a whole bunch of things because this is just a laminar calculation. Already non-trivial. Okay, so I think we've run out of time, so I'll start in the afternoon by asking about this problem. Very broadly, a little bit of this, and then in whatever remains, I'll tell you a little bit about specific instances where you have free surface problems. So far, the problems are not free surface problems, because I had bulk flow, no free surfaces. First question in the afternoon is, this is a steady state. Is it stable? This problem I'm not going to do, because again, it's going to be too much. I can, again, talk to people who are interested in knowing about this. I will solve two very simple problems, and I'll actually motivate you with this experiment. So this is a glass of water. And of course, everybody knows if I turn it upside down, it'll empty. And all I've done is taken, a piece of paper, just put it over here. Okay. Yeah, that's because I tilted it a little bit. I'll do it again. Okay? But it did stay. The point is it stayed for some time. Even that was non-trivial. So the question is, why? The question is, what can you essentially learn from this? And the teaser is, in fact, there is an instability. The instability is obvious because water is heavier than air, so it wants to flow out. But are all scales going to grow the same way? I mean, you also know that if I had a narrow tube filled with water, if that narrow tube didn't have too much water, then, or even if it did actually, then it won't come out. It's very hard to empty a narrow tube. It's very hard to empty a narrow tube, even if it's water. It's very hard to empty a broad tube if it's very viscous. So there are two kinds of questions. Question one, is a heavy fluid on top of a light fluid stable? And if it's unstable, which scale grows how? And question two is the second, is how does the length scale, how does the amplitude of any mode change as a function of time? Okay. That's a very, very basic question. A second question is, what would happen instead if I essentially, instead of having a heavy fluid over a light fluid, I had the reverse, stable, light fluid over a heavy fluid, but now I moved the light fluid. Okay. So the first question appears in the context of many, many physical situations. In science and engineering, in astrophysics, where we replace gravity by an acceleration, where I have an explosion, in atomic weapon design and so on. The second question appears when you look out of the window over the ocean, wind driving water. Okay? Light fluid, heavy fluid, wind is moving, you generate waves. What happens to those waves? How do they and I'll talk about just the tiniest beginnings of understanding the instabilities. I'm sorry I ran over.